how are things going so far? While we're getting the stuff set up, how's the class so far? Any comments, any suggestions, any critiques, any yes?
What are the homework assignments going to be?
That's a good question. They are almost ready. I'm basically cooling the homework assignments will cover basically recurrences, divide and conquer, dynamic programming, and greedy algorithms. So probably not greedy yet, but the first three groups. And I'm hoping to have them organized over the weekend. We've got a list of questions. I want to write out some sample answers so you all have an understanding of what it takes to sort of write a reasonable answer, what it means to answer a question. And so I want to put out a couple of samples there as well, and then once we have it all ready, like I said, we'll probably have, so today is September, let's see, today is September 11. September 11, okay. So I think what will probably happen is that we'll have a sort of a resubmission deadline. As I mentioned, you can do a resubmit. We'll have a resubmission deadline for about, probably early October. So the idea being, if you want to, you don't have to, but if you want to sort of get it submitted and checked, so you can do it again, you want to have it in by early October. But again, it's all purely optional. If you feel like it's fine. And again, there's no specific deadline for the homework, so we will just, you send them, the best thing for you, I would suggest to send them in as you do them. And then it'll be easier for us, it'll be easier for you, because you'll get feedback that'll tell you what to do for the next time. But there's no. Any other questions? Are we good? Yeah. So, do you happen to know when Tuesday's video will be uploaded?
I asked him and he said that it's processing and it's taking a little bit time to compress the video.
Okay, yeah. So we have the video from last week's lecture, and Tuesday's lecture the video will show up as soon as it's processed. It does take a time to process these things that you can compress them on the size and YouTube friendly and so on. But I don't know if have any of you tried to look at the videos? I mean, I tried to use them, apart from being entirely embarrassed by the whole process. The audio seems fine, the visuals seem okay-ish. I don't know what your thoughts are on the matter. Have you tried? Are the videos useful? So how many of you actually find the videos to be helpful, after class and sort of look at it and all? Some, not a huge amount. Okay, all right. Good. So you've now covered two of the three sort of what I think of as core tools in your arsenal for doing algorithm design. There are many more, but these are some of the most basic ones. Right? And they all come from recursion at some level. That you have, once you have a think about things recursively, you can do this what is called a divide and conquer strategy, where you break the problem down to pieces and solve these pieces using recursion and put them together. Then we also saw what happens when you do want to think recursively, but you don't want to implement recursively. And of course, dynamic programming is where that comes up, where you think of it as breaking it down, but you're looking for some more special structure of the problem that allows us to work. It's not always clear up front how to do it. And so a lot of dynamic programming involves either figuring out how to break or trying all possible ways of breaking the problem down. And then realizing that once you have to find all possible ways of breaking the problem down and you unwrap your recursion, it turns out to be a sort of a simple forward to backwards or sort of kind of filling up a matrix kind of strategy. And on Tuesday, you saw how to do things like the edit distance, which is an interesting example because now you have this two-dimensional dynamic programming concept. And in fact, dynamic programming problems come in many flavors. You can have multi-dimensional dynamic programs. It's a question of how many different parameters to your problem you have. You could have 4 or 5, but it's very complicated 5-dimensional table that you're filling in. And of course, at that point, you're not going to be visualizing so much as the details. And there are ways of designing dynamic programs to do that. There's also dynamic programming and graphs. I know John mentioned very briefly. I don't think we talked about it in great detail. I'm hoping the homework can explore some of that, how to do dynamic programming on a graph, which is also a very interesting idea that shows up in things like machine learning, for example. There are certain algorithms that work well because you do dynamic programming on trees and graphs and So having said that, we will now move to the sort of the third component of, I think, of this group of three tools, namely greedy algorithms. And if you want to think about, how they all fit together, the best way to think about it is in terms of drinks. So, divide and conquer is like milk. It's something that one of the first things you taste. It's kind of good for you, and it's kind of boring, but it's so good for you. You should really understand. Dynamic programming is like a health food, protein supplement. It's really, really good for you. It tastes horrible. Usually it's an acquired taste. You have to get used to it somehow. If someone tells you, yes, you really should learn, this is a very important thing, I go, okay, fine. And after a while, perversely, some of you start actually liking it. It's like this strange person who actually likes this stuff and who likes dynamic programming. And then maybe you start teaching algorithms one day. And of course, you can ask, well, where do greedy algorithms fit into all of this? Well, greedy algorithms are like Coke. It tastes great, everyone loves it, it's really bad for you. But in small doses, it's okay. Okay? And that's how you should think about this thing. And you can replace Coke by Diet Coke. It doesn't matter. The problem still remains the same. And what I'm trying to say is that greedy strategies are probably the most natural ways you might come up with doing algorithms. And again, first of all, what is a greedy strategy? A greedy strategy is something like this. You want to solve some problem, and usually you're trying to find the best of something, the smallest of something, the largest of something, often like what you do with the dynamic program. Right? So the greedy approach is what looks best right now. If I have to get from here to there, the greedy strategy says, okay, I have to get there, I'm going to walk right across, I'm going to go climb up on this desk, move right, I'll get straight there. Maybe not the best way to go. Sorry. But it really means, decide where I am right now. Based on that, do the best thing. So for example, if you're at the top of a ski slope and you want to go down, the greedy strategy would say, take the steepest way down. Don't take a turn, or don't go around the path of the nice marked green circles. No, just go straight. Okay? It's the fastest way down for sure. There are other problems, but it's the fastest way down. And so what it means to be best, and what it means to be right now, and what it means to be near me, are all things that define what an actual greedy algorithm looks like. And these are all things you will identify. And so conceptually, if you're thinking about a greedy strategy, it looks something like this. You have some kind of energy function or a cost function you want to find a smallest value. Right? So you start off somewhere at the top, and you say, okay, let's go down. So you go down, you go down, and now you're happy. And when a greedy algorithm works, this is why it works. There's some kind of basin at the bottom of which is your target, and you want to get there. And there's always a way to get there. And that's the key. There's always a way to get there. Which is not true if you're here. If you're here and you do this, if you're lucky to be in the right place to start with, you will get to the right answer. If you don't happen to be lucky enough to be in the right place to start with, you won't get to the right answer. The reason why people, or at least people who teach algorithms, caution about the use of greedy algorithms is you often don't know if you're here or here. And so the idea that, just doing what's best right now will work, only works if you're in this picture, and does not work if you're in this picture. Unfortunately, most problems are in this picture. And that's why it's important, even before I tell you anything about greedy algorithms, that be careful. But having said that, often you can prove that you're in this picture. And then your greedy algorithm will not only be the right way to think, it'll be a very fast way, it'll be a very easy way, it'll just seem very natural. Okay. And so the trick is, with a greedy algorithm, is knowing when to apply it and when the problem admits a greedy solution. So for a divide and conquer strategy, the goal is, okay, how can I divide up the problem so that merging is not too far? For dynamic programming, the problem is, how do I encode the problem recursively in such a way that I don't have too many subproblems to worry about, or that I can use the fact that there are not too many subproblems. For a greedy algorithm, the problem is, how do I phrase my step so that I can always prove that I can go forward and make progress and get to the optimal solution. So that's two things that are important. You have to be able to make progress, and you have to make sure you're ending up in the right place at the end. Once you do those two things, you get an answer. I'm not talking yet about running time numbers. Greedy algorithms, typically, the running time is not as much of an issue as correctness. Correctness is a big issue. The running time usually sort of writes itself from the way you design the algorithm. I spend some time per iteration, and the main question with them is usually how many iterations does it take to get to it. And so a lot of work gets spent. If any of you work in optimization of any kind, especially nonlinear optimization, if any of you have heard of something like gradient descent, how many of you heard of something called gradient descent? Many of you. Gradient descent essentially is a greedy strategy. And so you'll see a lot of the work on, it takes these many steps to converge, blah, blah, blah. The reason they talk about that is because that's really telling you how long it takes to get to something. No one can actually tell you whether it gets to the right thing. One of the things we will look at here in the next couple of lectures is how to reason about when it gets to the right thing. And then we'll also look at the analysis of how long it takes to. So let's think of a problem. Let's take a problem, a candidate problem that we want to sort of apply a greedy strategy to. And this is a problem of what is called interval scheduling. This comes up a lot in many kinds of, as a core sort of subroutine in many problems. And the basic problem here is that I have intervals, and you can think of this as, think of all these, the thing you're scheduling as some kind of shared resource. Right? Maybe it's, you work in a lab and it's a microscope that everyone has to use. Or it's some kind of, lecture hall that everyone has to use at different times of day. So this is time, and during the day, different people have different uses for it, and they have different durations of use for it. So that blue rectangle there represents the fact that someone wants to use this resource for this much time, from this time to this time, and then so on and so forth. So I've laid them all this way. And you're the planner for the resource, right? So you want to make sure that the resource gets used as much as possible. You don't want to be left idle. If you have an expensive microscope, you expect to be able to use it, do stuff with it, or if you're a lecture hall, you want to be able to use it. So you want to be able to schedule all these people so that you can maximize the amount of time it's actually being used. But of course, there's conflicts. And if you're the planner, you want to somehow, obviously you can't schedule two people at the same time. So what you might like to do is say, okay, you can schedule these two together. They don't conflict. They have different times, that's fine. Or you could schedule these two together. You could even be more clever and do these three. And that's slightly better because you've got one more job in, and there's still not conflict. So this is a better schedule than the previous one because I have 3 people who are now happy with me instead of 2. What you don't want to do is do this, because now you get a conflict. Right? So the problem of interval scheduling is, how do I, given my input is a collection of intervals along the line. So each interval is a start point and an end point. Think of it as starting point. And what you want to do is pick off some subset of them of largest size possible so that they don't interfere with each other. Okay. That's the problem. And that's called interval scheduling. Another question is, if we wanted to solve this problem, this is one of those problems again that admits many different kinds of plausible greedy strategies. And we can look at some of them and see something that sounds reasonable. Say, okay. For example, you might say, pick the one that starts first. Let's get it out of the way, and then move on to the next one. It's a local strategy because you can say, I'll pick one, run it till it's done, and then pick the next one that's available. So that's what makes it greedy. It's greedy because I'm doing the thing that starts first somehow to me seems like, okay, I really want to pick this one first because it's already going. I don't want to waste time and pick someone who might start later because my room's not being used. So I pick the one that starts first, and then I run it. And it's not hard to see that this is a bad idea. In this example here, the algorithm that says pick the earliest one first will pick the blue interval, which will monopolize the microscope for the whole day. It's like a bunch of print jobs and someone is printing out a PhD thesis or something on a single page. I'm sure this happened to you way more. And so you'd want to pick the smaller jobs first, right? So you say, okay, good, we should try to pick smaller jobs because you can fit more smaller jobs, right? And this is telling you what to do. That doesn't work either. Here, picking the smaller job is a bad idea because now it's blocked off too much bigger job that you could have picked. And by the way, I'll give you another example of this, but with greedy algorithms, we do this a lot. Because they're so easy to design, the trick is to figure out when they don't work and to try and break them. And slowly in the process of failing to break them, you realize how you might try to actually prove that they are correct. But whenever you design a greedy strategy for a problem, your first goal should be to break it. And sometimes it'll be easier to break. And then you would realize, okay, so something's wrong, I need to change right here. And sometimes there may not be a greedy strategy at all. But that's a different story. So here's another strategy. Pick the one that ends the earliest. Now this is not a counterexample. I mean, you just pick the blue one over the red. It's not completely clear whether this will break or not. There's no, at least I don't see an obvious counterexample. So maybe this survives the next stage. You know, this was like the American Idol of greedy algorithms. They got knocked early to this next level. They get to perform in front of a live audience of people who are going to break. So we have now a strategy. And again, it's a greedy strategy because we're sitting here deciding, making a local decision about what step to take next. I'm not designing a plan. I'm not designing a recursion. I'm not giving an overarching view of what the algorithm is doing. I am merely saying, let's do this first, and then we'll see what happens. And this is the essence of what a greedy strategy is. You don't plan out the whole thing. You just make one move, and making that move might now change the configuration in some complicated way. So then you reevaluate. Okay, now what is my best move? You make that move again. Okay? So it's a constant updating and reevaluation. So it's merely a local plan. It's not a global plan. It's like when you go to if you know this thing about going in a maze. If the entrance and exit are on the edge of the maze, one strategy is always go left. I wouldn't necessarily call it a greedy strategy, but it's definitely local in the sense that I'm not giving you a plan to the maze. I'm just saying at every step do something simple, and then do it again. And that's the flavor of these algorithms, which is why they're so attractive. They're very simple. It's almost like a finite state machine, and every state do something. You don't even read. Okay, so let's get back to this thing. What do we do with this? How might we reason? You know, maybe we've tried a bunch of examples, nothing seems to break, and now we're frustrated. We don't know that it's wrong because we found a counterexample, but we have no idea if it's right either. So what we want to do is reason about how we might prove that this is correct. Yes?
It's our aim to have as many jobs as possible.
Yes.
Not trying to get the time utilized as much as possible.
The aim is to have as many jobs as possible. In this model, you could think of the jobs as your satisfied customers. You want to satisfy as many customers as possible. There are twists to that. We'll get to that. But yes, you could ask a really good question as well. And some of these questions get very hard very quickly. So it turns out this does work. If you have unweighted intervals, which means all your customers are equal. Everyone who wants this room is as important as everyone else. Which is a big fat lie, but anyway. This actually does work, and now I will show you how to prove that it works. It's not enough for me to just say so. And the way there are basically two strategies, more or less. I mean, there are all sorts of variations, but there are two strategies to show that a greedy algorithm is actually correct. And before I even talk about it, let's think about what that might mean. How would we show that a greedy algorithm gives you the optimal solution to a problem? When the greedy algorithm is not even an algorithm, it's just a sequence of steps. How would we go with this? Remember that with a recursive strategy, we used induction. We said, okay, let's assume the algorithm was correct for smaller levels. Let's say we have a divide and conquer method. We'll show that the algorithm is a correct merge of correct answers, and therefore it's correct by induction. With dynamic programming, we did essentially the same thing. Assume there was some kind of way to order the way the dynamic program was working. Either on a line you had stuff before or you had stuff after, or in 2 dimensions you had kind of the initial part of your matrix. And so you say, okay, by induction, assume that things are correct so far, then the next step will also be correct by the optimal substructure property of that. We don't really have that kind of luxury here. We're not doing a divide and conquer. There is a sense of induction because we're making more and more steps, but it's not completely obvious how we would build such an inductive algorithm. So what do you think we should do?
We would assume it's not here.
Yes?
How about negation? Like you see where you try to find out the cases where it's not going to work and see whether those cases are possible in what scenarios.
So you want to prove by contradiction?
Yeah.
So you want to say, let's suppose my algorithm is not optimal, right? Then we will prove a contradiction, right? Okay? All right. That's one idea. Yes? What else? Yeah?
Proving that making that first step doesn't preclude you from finding the optimum.
It doesn't preclude you. What does that mean? Can you spell that out a bit more, a few more words on that? It doesn't, so in other words, you're trying to say something like it's not a bad step to take.
Yeah, or that there is some optimal solution that uses that as its first step.
Okay, good. So you just took your sentence and made it a little bit more precise. So the first thing you said was somehow show that taking that first step doesn't preclude you from getting the right answer. You didn't go off in the wrong direction, right? The second statement, which is a refinement of this, says, in order to show that you didn't go off in the wrong direction, I somehow have to show that that is in fact the right direction. That there is an optimal solution that would go that way as well. And that's in some sense how these things are going to work. We're going to say something like, we're going to combine this with induction. We're going to say, okay, the algorithm takes a certain number of steps. That's going to be our inductive parameter. Let's assume that up till now the steps it's taken, the algorithm is in fact as good as the optimal solution. Now we're in a good situation because now we can, the algorithm itself is take the next step, right? So now we can say, okay, when we take that next step as the algorithm tells us to, can we still show that we are as good as the optimal solution? And one subtlety about greedy algorithms is that you're not proving that you get the optimal solution. You're proving that your solution has the same cost as an optimal solution. There are, in that example of the intervals, there could be different solutions of size 3. I'm not claiming that I match any particular solution of size 3. I'm claiming that I match some solution of size 3. Okay? And that's an important point. Okay, so how is that going to work? So let's say we have an instance here. Okay? And so let's first run the algorithm. So at this point we take this first. This is the one that ends earliest of all the inputs, so we take that. Now these two are precluded, we can't pick them anymore. So now what's left? The next one we can take is going to be the one that ends the earliest, which is this one right there. Right? So we take that one. And that precludes this one right here. Then again the next one that ends the earliest is going to be that one right there. Yeah. So we take that. That precludes this one. And the next one we take is going to be the one up top. And then it precludes all of them. And that's the solution. So this is how the algorithm will run. And you could probably already think in your head how you're going to implement this. You're going to sort them by all the same time. You're going to eliminate things from the list of the contents. It's not too hard to do. Okay. So again, as I said, show that at each stage of the algorithm, it performs at least as well as the optimal solution. And this is how it's going to work. So here's how the argument works. Let's say we add the jobs to the algorithm in the order I1, I2, I3, where I is the index. So we have the jobs labeled 1 through n, right, the intervals, and we add first job number I1 to the algorithm, then I2, then I3. So we know what the algorithm is doing. We have its whole history. It's a deterministic strategy. And let's say we don't know what the optimal solution is, but there's some optimal solution somewhere, and the jobs are added in order J1, J2. Okay? Again, we don't know what optimals, but we're going to reason about it. And let's say that's S and F are the start and end times for start and finish, or the start and end times for each of these. So here's the claim we have. The first claim we're going to make is that at every step of the algorithm, okay? So you've made k steps, the opt has made k steps. Notice that we can pretty much assume that we pick this, so at every step, the first step, second step, third step, whatever, the finishing time of our last job is earlier than the finishing time of the optimal job, or at least it's less than or equal. The informal version of the statement is we always have more buffer room than opt. If the opt schedule at this point is ending at time 10, our schedule is ending at time 9. Or it's ending at time 10, but not at time 11. And this is important because, as we'll see, this is what gets the idea of we can continue to do what opt might do without being prevented. Let me explain what's going on. So this is the claim we want to prove. And again, we'll do it by induction. So base case, Why is this true in the base case? It's true by definition. The greedy algorithm always picks the job that ends the earliest. So after one step, we had to have a better ending time than opt. It could be the same job, that's fine, but it's no worse. Right? Yes? For one step, just one step. And okay, so now we start the induction machinery. Assume it's true for all k less than r. So now this is, and let's assume that the finishing time of the R job is actually worse than the finishing time of the ops. So we're going to prove that contradiction. So we want to prove that it's always the case that R finishing time is less than opt finishing time. So see, we'll assume it's not true. Assume that R finishing time is in fact after opt. So the picture we're going to get will look something like this, right? That we're claiming that after R steps of the algorithm, the last job of opt ends there and R job ends there. This is the situation we want to prove is not possible. We're proving this by contradiction. Okay. Okay. So remember, we're in the middle. We're deep in the middle of an induction argument. By induction, we've proven the base case, and we're assuming by inductive hypothesis for all values less than R, it is in fact true that R ending time is before ops ending time. And now we're saying let's assume by contradiction that in fact after this step we made a mistake, and R ending time is worse than ops ending time. Yes.
So the optimal is I and
J.
optimal.
Where are? So let's look at what happened in the previous step. Okay. By the inductive hypothesis, we know that the previous step we were good. So our picture looks something like this, right? That our last job ended before ops last job, right? Okay. Now what? So here's what we're claiming. We're claiming that our algorithm got to I R minus 1 and then picked that one there. Whereas opt did this, and now opt is better than this. I'm claiming this can't happen. Can someone tell me why this cannot happen? Yes?
If we are going at fi r minus 1, after that this step will work.
Pardon me?
I mean, the ending time of f of I r minus 1, after that we will go and check in the optimization.
We will go and check it.
In the second one.
You're saying you will pick the second one?
Yes.
Why will you pick the second one?
Because that is how the algorithm works.
It always picks the. But suppose because of some weird constraint, we can't pick that because it's conflicting. But opt will. Is that possible? I mean, we pick the least ending one that doesn't conflict with what you've already picked. Can this conflict with anything we picked so far? No, you're saying you're shaking your head. Why not?
Because its start time is later than fg minus 1.
The start time of the new job is later than this, which is later than ours. So if opt could pick it, we surely can. Because we ended earlier. And that's where the magic is happening. Because we ended earlier than opt up till now, we have the freedom to do what opt could do, which is like what you were saying. So this situation cannot happen because the algorithm would in fact pick JR for its next step, it would not pick R. So to claim that the inductive hypothesis is true and we make a mistake here is a contradiction. Therefore, this cannot happen. Therefore, the inductive hypothesis continues to be true for R as well. Yes?
Would our algorithm have to also stipulate that our start time for our next job has to be later than our end time of our IR minus 1?
Yes, and the way we've said that is that once we pick a job, we remove all jobs that are in conflict with it. So automatically, it will eliminate all the jobs that would have that problem, right? Because their start time would interfere. Yes? Okay, so these kind of things can be a little, slippery. They seem like they make sense, but maybe then suddenly you leave the room and the kind of the cloud of understanding that I was projecting is not all doesn't make sense anymore. So, what do you think of this? Kind of sound reasonable? And again, the mechanics is what's important here. There are lots of details here, of course, but the mechanics is that we are trying to reason step by step about what opt is doing and saying that we're always ahead of the game, or in this case, behind the game. It's like we're running a race with opt, and we're always saying, no, we're always behind. So we all got more room to go. So we're always safe. And so to wrap up this whole argument, right, once we've done, is there a question? Yes.
What does that mean? We are the optimal case. If we're behind optimal, aren't we optimal? What is this? I don't understand. Like by this, we could never be in front of optimal. Where is this?
So we can never be in front of optimal, and opt is opt. We should be opt.
Yeah.
That's a very good question. But someone like yes.
There to be more than one optimal solution.
We're not arguing about the actual set of solution. We're just arguing that if opt could do something, we could do the same thing too. Yes.
So why do you say that the greedy algorithm cannot achieve the global optimum?
Well, in this case it will. In this case it will. Not in general.
So the way that actually we are going to prove that we are doing solution is we say that assume that there is an optimal solution, so we are not worse than that. So
Yes.
when we use this way to prove that the greedy algorithm works, it means that we are always the global maximum.
Yes.
So there are other ways to prove the greedy algorithm.
I think maybe you're asking why doesn't this always work? How can there ever be a situation where we're not the global optimum? Is that what you're asking?
Sorry?
Are you saying why is there a situation where we're not the global optimum?
Yeah.
Why would a greedy algorithm ever fail? Is that what you're asking?
I'm asking that what are other possible solutions to actually prove that greedy algorithm works?
We will see one more. We will see one more after this. There are not too many. There are basically two in the variants, but we will see them, which almost looks like this, but it's like. Good. Any other questions? We're not quite done yet. Some little bookkeeping has to be done. All we've proven at this point is that at every step of the way, we are behind opt. Right? So you have to wrap it up by saying that at r+1. So suppose the algorithm has cost r. The algorithm gets you r inputs, r intervals as a solution, and opt has more. Right? But then again, we know that we can keep track with optimal every step of the way. If somehow we stopped early and opt could go on and pick more things, then that would be a contradiction because we just proved this. Right? So there's a minor bookkeeping detail, right? Essentially we proved the point of the induction, but you have to say, okay, I think all we've done is we kept track of optimal's point. What you want to say is that opt can't just keep going while we stop.
You mentioned once about the greedy algorithm that the solution that we find may not be the optimal,
May not be in general. In this case it is.
but the cost would be
The cost is optimal cost. That's what we're proving here, that the cost is the optimal cost. That the size of the set is the same as optimal. We're not saying that the set is the same as optimal. So we'll get a solution of size 3 in that example. Opt might get a solution of size 3. Opt will never get a solution of size 4. But the optimal solution of size 3 may not be what the algorithm produces. The reason also is that, for example, you could have things could have tie-breaking rules. You might pick one thing versus another thing, and there are many different ways you can combine things up depending on the greedy strategy. You might have two different greedy strategies giving you two different optimal solutions that are the same size. Does that make sense? Or
actually I'm not able to figure out
why would that ever happen?
Yeah, if the cost of the solution is same as that of the
Let me see. Actually, let me see if the example that we have there will admit such a thing. So I think we said the solution was size 4 because you click 1, 2, 3, 4, right? The three middle ones and the one at the top. Can someone come with a different solution of size 4?
Yeah.
Okay. Yes. Okay. So there are two solutions here that are both optimal. The first solution, and I don't know if this. Can you see this laser pointer? I hate laser pointers. Can you all see them? The first solution that we found was 1, 2, 3, 4. Right? Another solution that would not be found by our greedy algorithm, because our greedy algorithm doesn't work that way, would be 1, 2, 3. So in fact, this is a good question you asked. Let's pretend that the first solution, of course, is what we found, and the second solution is the opt solution we're comparing against. Okay? So at step 1, we pick this. Let's say opt pick this. our finishing time is earlier than Bob's finishing time, so we're happy. At the next step, we pick this and Op picks this. Our finishing time is before Bob's finishing time. At the next step, we pick this and Bob picks this. Our finish time again is at the end we both pick the same. So even though at every step of the way we are not the optimal solution, we are always behind it. So we always have the chance at some point to switch over. It's okay, fine, we'll do it opposite. In this case, it happens right at the end. But as long as we're behind off, we don't care what the solution is that we make. All we know is that it allows us a chance to switch over to the optimal solution at some point. Does that help? If there are questions that everyone's sort of getting at? Yeah? That makes sense? Okay. Good. So this is one, again, example of how you prove that a greedy algorithm is in fact optimal. That at every stage it's at least as good as optimal. Because at every step it's at least as good as optimal, then at the end it has to be optimal. There's no room for maneuver. Okay. Let's look at a slightly different twist on this problem. Alright. So this is a different variation of this, where again we're doing scheduling, but our goals are different here. Now we have a number of tasks, and each task will take a certain amount of time to perform. Let's say these are different homeworks in your different classes. You have different deadlines. So you somehow, and this is completely not true in practice, but in principle, you actually know how long each homework is going to take. And you have a good estimate of how long it's going to take. And so you have some job which has a length, the time it will take, and a deadline for it. And now your goal is slightly different, in that you have to schedule the jobs, all of them. You have to do them. All of them are homework. And you will get late, presumably, if you don't do this properly. But you don't want to be too late. You want to minimize the time you go over. Right, so some job is going to go, or maybe more than one is going to go over. You look at the total time it takes before you finish the whole thing. That minus the last deadline is your lateness. Like I said, lateness is for every job. In fact, if every job is late, every job you can be late on if you pick the wrong order. And then for every job you have some lateness, you add them on.
And there's definitely a solution. Is there guarantee that they'll all fit in the time?
No, there's no guarantee. That's why you go late. Oh, you mean, is there a feasible solution that there's no lateness? No. Maybe there's no way to solve this one. Maybe you're, as everyone, like, professors give you too much work. There's no way you can finish all the time. So the question is how late you want to be. And that would be useful if you go to your professor and say, look, here's my solution to the problem. There is no optimal solution with zero lateness. What are you doing to me? I would concede to that point if you could do that. Or I might question your estimates. So does the problem make sense? That now we can't choose a subset of things to schedule. We have to schedule all of them. And therefore we will go overtime on each of them. And they have their own individual deadlines. So for each job you look at how much you went overtime and then add up all the numbers. And in this case there is in fact a schedule that gets them all. You schedule this one first, this one next, this one this, and in fact this is zero lateness. Okay? Alright. And once again now we can think, what would be a plausible greedy strategy for this problem? So again it has to be something that's a local step. You make one move. Yes?
Find the task that has the earliest deadline.
That has the earliest deadline. Hold that thought, we will get to that in a second. What else? So earliest deadline is 1. What else? Yes?
The most important task is waiting.
The most important task is waiting. That's a good one. Only catch is here, I haven't said anything about importance. I'm pretending all the jobs are the same importance. So now if you say they're all equally important, is there a way you want to change that strategy a little bit?
The one which completes purchase.
So one second. So, sorry, did you want to adapt your strategy given that they're all equally important? What do you do then if they're all equally important jobs? So maybe the one that has the longest list? Okay, so you can say do the most difficult one. That's a good strategy right there. That's definitely a valid greedy strategy. Decide your thing, which is the longest one, take that one. Okay, yes?
The
difference between the length and the deadline.
The difference between the length and deadline. So the job that's most critical. Is that what you're trying to say? If the job is like got. So yeah. So which way do you want to do this? Do you want to take a job that
The
is
maximum time, for example, I'll pick the task 3 first.
because it has the most time to the deadline?
Yeah.
Okay. So you want to pick the job that's good. Okay. There was a hand up in the back somewhere. Yes.
Yeah, it was the same. We can relate the length with the deadline. Maybe we can start with the shortest length and immediate deadline first, because
Wait. So you're looking at length or deadline? Which of the two? Are you looking at subtraction?
some relation between the length and the deadline.
Some relation. You're not
Yeah.
specifying which one exactly, but some relation.
It could be that the shortest length and immediate deadline first.
Right.
Yeah, and,
Right.
and something like.
Very good. Is any other suggestions? Yes.
Do the shortest job first.
Do shortest job first. Very good. These are all very good greedy strategies. And they're greedy because they say, look at the input, make a decision, do it, and then reevaluate. They're all that way. Right? And it's actually, as you can see, it's not, it's not too hard to come up with a reasonable strategy like this. And then again, you could imagine it like this very easily. And therefore, the question is always going to be, which of these is actually going to work? And that's what you figure. So let's look at some examples. So let's look at this one of scheduling the shortest job first. I think that was one of the suggestions we had. And let's look at this particular input. So let's see. If you schedule the shortest job first, you're going to put this job first. Then after that, you're going to slide this one over here. Right? And so this job has got a tight deadline. It's going to go over its deadline by 1 unit. Of course, what you should be doing in this particular case, and I have the benefit of hindsight, so you look at the input, you say, oh, well, in this case, you should have put this job first and then put that one after because deadline's later. Of course, there's no way to know that that was the right thing to do. But at least this shows that scheduling the shortest job first has one problem with it, that it may not give you the optimal solution. The optimal solution cost us 0 because we don't have any later. Does that make sense? Okay. I think this one came out as well, the least slack. I think yours was maybe the most slack. Right? You had said the most gap between time and deadline. This is the opposite of that. So what you're saying is the job that's the most critical to you, you schedule it first. Because that needs to be done. And so you do that. The job which doesn't have that, it's not that critical, you don't. Here, because of the fact that you schedule this job first and it's long, that one gets pushed way out to the end and its latest is 4. But if you do that one first, this one gets late, but only by 1 unit. So the optimal solution is 1 here, it's not 0. But your solution will have a score of 4, which is very low. Okay. And let's look at this strategy. I think this is what you're proposing. Increasing order of deadline. So this one says, schedule the jobs in the increasing order of their deadline. Which is very weird. We're not looking at the length of the job. It somehow doesn't matter. That's very strange. If you came to look at this problem, you wouldn't think that that would make any sense. And you'd be right to be very suspicious of this. And like any of the other solutions, we have to somehow break this. So this is ignoring the lengths. So the question is, can you somehow play with the lengths to make this do the wrong thing? And again, the wrong thing doesn't mean things get delayed. The wrong thing means things get delayed and you could have done it better. Yes?
Are we allowing jobs that take longer than their scheduled time?
There is no reason to exclude that possibility, although it's kind of weird. But weird in the sense that if someone gave you that, like, what are you going to do? I can't do anything. But there is nothing in the problem that says this is not allowed.
Okay, so that's a way we can look to try and break it.
Schedule, okay, have jobs whose length is more than the deadline.
Mm-hmm.
Okay, that's a good idea. How do we come up with a counterexample for this based on having jobs that go longer than the deadline? Because it might be this algorithm actually breaks. This algorithm is allegedly correct, but it might actually break if you do this, which would be cool to see. Okay.
So,
Yes.
The objective is to reduce the
Total lateness.
total failures, right?
Total lateness means per job. So for each job, you see how late it got. Then add up the lateness for each job.
If I have 3 jobs which have the same deadline
Yes.
and have same amount of work,
Yes.
And then the fourth job which I have
Yes.
has a late deadline, but has a very small work to do.
Yes.
Then since I'm seeing these deadlines first, I'll try to do all the jobs which are close to the deadline.
Ah, you'll do only one of them.
I'll do, because all the three are less.
Right, but pick the job which has the earliest deadline.
Earliest deadline.
So you'll pick it.
Yeah, and then I'll pick the second one, and then I'll pick 2, 3, and 4.
Okay, so let's draw this. I will draw this because I'm behind the screen. Oh, I could draw it, but it would be a little complicated. Let's see if I can do this. Hold your breath. It's going to be exciting.
You need to steal your son's tablet again.
I did. I stole my colleague's tablet, which is way better.
Okay.
My son is less forgiving than my colleague. If I could just move this thing out of the way. Okay, I can't move it. Let me. Okay. Sorry, I can't move this out of the way right now, but I can definitely change the color of it. Okay, so let's see. So you said we have 3 jobs that end at the same time.
We have 3 jobs, so deadline is 3 units, and the work is 1 unit.
Okay, so let me draw the deadline. Let me draw a number line here at the bottom. Okay. And now you're saying that there's the deadline is here at 3.
Yeah, for 3 jobs.
Okay, and the 4th job?
Oh, sorry. I have 3 units of time, but the work is only 1 unit.
So the job start at time 1?
One job starts at time.
But it doesn't matter when they start. The point
Yeah.
is it doesn't
So I
matter.
have 3.
Okay, yeah.
And then I have 1 job, which is deadline is longer,
Okay.
which is like 6, let's say.
Let me be even more ambitious and try to put a color on this. Okay, so its deadline is 6. Okay, and its time is
And the job is 3 units. Oh, wait, sorry.
You can make me erase now. My tech skills are not that good.
Oh yeah, now just, okay, sorry.
Is this input correct?
Is this input is a little bit wrong. The first one deadline is 3 units, last one deadline is 6 units. Now you're good. Sorry. There's a very trick. Sorry.
Fine. There's allegedly an eraser somewhere here.
Yes, you have an eraser.
Large eraser. Okay. So what am I supposed to erase it for?
There is a red deadline.
Yeah.
Put it near the black, and the black deadline goes to red.
So all the black deadlines go, or just one?
All the black.
All the black deadlines go away.
And
Okay.
they go to the last.
And they go to the end. And no, I'll do all the erasing first. So
And erase the red line too.
erase the red line. Okay, I can do that. Okay, now what do you want me to do?
And the red deadline is just when the job ends.
It's right here.
Yeah. And the black deadline is at the end.
So these are all 1 unit, right? These jobs.
No, sorry, my guess is
Excuse me. Yes, you were saying.
sorry,
As you will see, coming up with counterexamples is not easy. It's good. I mean, I'm joking here, but this is a very good process. Coming at counterexamples is hard. So are you correcting yourself because these are not actually turning out to be counterexamples?
I had one example which I felt it was.
How would we stop with an example? If it breaks, we can come up with another example.
Okay.
If we fail to break the algorithm with counterexample, we can come up with another one. So is this an example that we can live with for now?
Yeah.
Okay. So they all have the same, let's take this example, they all have the same deadline. Their claim is that the algorithm that chooses the earliest deadline first will break. So what is the algorithm going to do in this input? They're all the same deadline. So there's no way to type break. So it'll just pick whatever order you want. So it will pick this one first, or this one, and this one, and that one. Right? The total duration will be 6. And that job will be 3 bits late. And the rest of them will be 0 late. Total lateness is 3. Suppose I picked in a different order. Suppose I pick that one first, and then put all these 3. That job will have 0 lateness. The first one will have 1, 2,
1 plus 2 plus 3.
huh. Maybe this is a good example. Okay, so let's see. So the claim, so let's say the solution here is going to be,
English one of the
no, wait. Let me just draw the solution here. So the solution is going to be, is that right? Maybe I got my measure wrong. Because this has lateness of 6. What I really want to say is a lateness of 3. Because you end. Well, I don't know.
Certain the smaller blocks be still
Sorry?
the smaller blocks are just one, right? So they, I mean, be on the left.
Sorry,
Deadline on-
can you just settle up? Yeah, sorry, I didn't hear you.
So regardless of what order you start with, you want to have the latency for you to start with the smaller blocks because they start on the left. They take 1 unit at a time, their deadline is the same deadline as where the red ends. So you can do 3 of the smaller ones before.
Right, but my algorithm currently is unspecified. My algorithm just says pick the one with the earliest deadline first.
Right, but they have the same deadline.
Right, and so my algorithm is incomplete because it does not specify what to do with
But you
this.
get the same result regardless of what one you have. You're the smaller blocks can be drawn to the left.
But how do I? No, but it's not that, right? I mean, the actual locational block doesn't matter.
Right.
All that matters is length is 1 and its deadline is 3.
So right, so the red is a unit further, right? So you can do the 3 units of the 3 smaller ones first.
I could, but I have to tell my algorithm to do that.
Well, it doesn't matter. It's the tiebreaker, right? Because they have the same deadline.
Right, but my algorithm. So what I'm saying is that my algorithm without a tiebreaker rule could produce the schedule.
Right.
But that would be wrong.
What's the latest?
Well, that is the optimum solution. You get that.
The latest of this is 6. This is 1 unit late.
Yeah.
This is 2 units late.
Uh-huh.
And that's 3 units late. So I need a tiebreaker rule for this. And maybe the tiebreaker rule is to say the jobs that are shorter go first, if they're all the same deadline.
How do you get 6?
Sorry?
How do you get 6?
That would fix this because then these would go first. They're smaller. So if I said schedule the job with the earliest deadline first, if there are more than 1, pick the shorter. That would be my new algorithm. And that would fix this problem. Doesn't mean it's correct, but it will fix this problem at least. There are lots of hands going up here. There's a hand back there, yes.
If we change the example to have 2 jobs with 1 unit of work, and we choose first the ones that are smaller, and then the third one, compared to the case that we choose the smaller one first and the bigger one second, the actually lateness to be different. Here they're the same. Both of them be 6 units, but at that case,
No, this would be, no, if you had only 2 of these, then this would be 1 plus 2, 3 units of lateness. That would also be 3.
Yeah, but when we choose the jobs with the actually shortest, the jobs that have 1 unit of work first, the lateness will be different.
Right, it would be less. Right, this would be 3, that would be 1. So in fact, I think that's the right, that might be the right strategy. So to say, if they have the same deadline, pick the shorter ones first. That's quite possible that's what's going to happen.
Yeah, because the location actually that we have here is a difference between when the job ends and...
There's no notion of the job ending and starting. You can slide it whatever you want.
I
You
know,
just have a deadline for
but
it.
the way actually we calculate the cost, if you consider, we should kind of, design the algorithm, we should kind of consider the difference between the time that the job ends and the deadline. And
Yes.
these are the things that actually...
That's what I'm calculating. That's exactly what I'm doing.
Yeah.
Okay. All right. This is good actually. This is an interesting twist that I had not yet that I had not discovered before. But let us go back to the actual algorithm description itself. For now, let's say that we will use the algorithm that was proposed with this tiebreaking rule, and let's continue trying to reason about it. Unless you can come with a counterexample with the tiebreaking rule as well. So the new tiebreaking rule is if there
If you take the black ones, if you move the deadlines to 4,
Yeah.
then the lateness will be 3, where if they came first, lateness would only be 2.
Which is again, but that merely reinforces the idea that we should have that tie-breaking rule saying put the short.
If you move the lateness of the black ones to 4, but keep the red one 3,
Yes.
so that the red one comes first,
Yes.
then the lateness would be 3, because the 2 black ones will be late. One after the other, so the 1 and the 2.
Yes.
But if you were to put the black ones all first, even though their lateness is 4 and the red one's lateness is 3, then the red one would be over by 2, so the lateness would be 2.
Yeah.
You could go by 3.
Pardon me?
I think ours would be over by 3.
So let's draw it. I think it'll be easier to draw it. So let's draw it. So what we're saying is that we have 3 jobs with a lateness of 4. Is that correct?
Yes. Right, no. So you have a job that takes time 3.
And has a
like that one.
Yeah. So let me draw that one first, since we all agree on that one. So that clearly is a problem case. So there's one job that has 3 units of time.
Yep.
And has a deadline of 3.
And then you have 3 jobs that take 1. And their deadlines all are 4.
Okay. So the strategy that says sort the job and schedule the jobs at the earliest deadline first will produce this solution. So it will produce a solution. Then you draw this properly. Okay. And the solution that says put the shortest ones first, I guess.
The shortest.
Oh, you're not saying, you're right. You're just saying there exists a better strategy, which is to in fact put all these guys first.
Yeah.
That's right. Fair enough. Oh, okay. I didn't draw this right when it should be here. And put that one next. Which makes me feel that I think I proposed the cost function for this algorithm wrong. I think the right cost function should be the total lateness, not the individual summed up latencies. I think I may have got this wrong, and that caused all this. But this is good because you could easily imagine that other cost function. And now I have to think about what is the optimal solution for that. So, yes?
Doesn't this know both the solutions give the same lateness?
No.
This is a lateness of 2, right? Oh!
3.
It's also 3. They're both 3. Good. Why is it? Because this one, these 2 are late, and this is 1 and this is 2. In this case, this one is late, but this was deadline of 3. Yes?
Can you add one more red?
Good. Where do you want to add it?
Right, like the same red.
Okay, but what is length and deadline the same?
Then exactly same.
Oh, okay.
Just one more red.
I can do that. I'm the guy with the pen, so I can do whatever I want. Okay?
So now since they end first, so 1 and 2 will go together, like first 1 and then 2.
Yes.
And if you have many more such, then those smaller blocks will be like left because you are choosing the earliest deadline first. In that case, the latency for those smaller blocks will be too high.
Yes, but is that also true for the optimal solution? Yeah, I mean, it's not enough to say this is too high. You have to say it's an optimal solution that does better. Can you say that?
I'm just trying to say that it won't be good with your strategy that we schedule the immediate deadline first won't work in this case.
I'm not yet convinced of that because you haven't shown, to show me it doesn't work, you have to show me that this strategy gives you a solution and then there's a better solution.
Yeah, so if I choose one red and then one black,
Yeah.
or some blacks, then red, then it will be a better solution because the latency for the blacks will be less comparatively. If you use red, red, then black, then that black will be very
Suppose, as I've been saying now for the last, as I've been proposing, that I change the cost function to not be the sum of the latencies for the individual jobs, but the total latency. I wonder if that would change things. That doesn't make sense. Really, okay. Let me go back to the slides for a second. Because I'm confused with it.
Google.
Where's my slides?
You made it okay.
Didn't you make them invisible?
Sorry?
You made it okay. So you need to un-okay.
Yeah, but I don't want the drawing on the thing anyway, so let me just put this. One second, let me just check something. Hold that down. I figured out what I did wrong. Okay, I figured out the problem. I just need to now get my technical problem solved. Sorry. This was my mistake. I defined, and this is a good, well, I don't want to claim that every mistake I make is a good lesson for you. It's also a good lesson for me not to make mistakes. But in this particular case, changing the cost function can make a big difference. The correct cost function for this problem is not the total sum of the delays. It's not the total delay, which doesn't make any sense. It's minimizing the worst. Now suddenly it all makes sense. So in other words, the cost of this is look at the delay for each individual job and don't add them up, take the worst of them. Now in all those examples, what's going to happen is that in the case where we had the 3 and the 1s and the 1s and the 3, one job is going to have the worst delay of 3. Same as the red job, which had the worst delay of 3. So they will all have the same cost. And we will not have this problem. But this makes me wonder whether what happens if we now change the cost function. And that usually when I say that means in my net it was a homework problem. So, but sorry, I apologize for the confusion. The goal is to minimize the worst case delay, which means you look at all the jobs after you schedule them, look at how much delay each of them has, and take the worst of these. So you want to make the most unhappy person as happy as possible. Does that make sense? And again, I'm sorry about the confusion, but does this new cost function make sense? Can you guess?
You mean we need to make to find the minimum difference between deadline and length of job?
You look at the schedule. Okay. Look at the job which has the worst gap. That's your cost. You want to find a strategy to minimize that number. So again, let's go to our examples. In this case, again, the same thing. If you schedule the largest, shortest job first in this new cost function, you will schedule that job first and that one next. Its lateness is 1. The other job lateness was 0. So the max of 1 and 0 is 1. So its lateness is 1. Yes.
So if we're looking at optimal solutions, then is there a way to tell what is optimal at each step? Because we can only analyze the optimal solution at the very end, right?
That's the problem. The problem is the greedy strategy is you have to reason about properties of the optimal solution without knowing what it is. This is like what we did in the last example. We said the optimal solution, no matter what it does, by using this strategy, we keep abreast of it. So we're always behind the optimal, we're winning. Here we're going to make a different argument. We're actually going to reason about the optimal solution.
I guess. Yeah, what else is that? As you said, we would have some measure what else the optimality.
We don't really, so that's hard because okay, in a greedy algorithm, the reason why a greedy algorithm actually works is because at some level you can say that. But it's often very hard to say exactly how good you're doing so far. But at some level, that's the only reason why greedy algorithms work. Because local operations you make only change the optimal solution locally. You don't make a big change in the optimal solution. And maybe this is too high level an answer for you. We can discuss that later. Alright, so let's go back to our examples again. In this case, the maximum lateness is 1 if you schedule the shortest job first, and if you reverse the order, the maximum lateness is 0 because you can schedule all of them. Correct. In the second example, if you schedule a job with the least slack first, you would schedule this one first, and that one next. That would be 4 units late. This would be 0 units late. The max of 0 and 4 is 4, so this would be. And if you reverse it again, this would be 1 unit late and max of 1 and 0. And now let's go back to this model. We're now going to schedule an increasing order of deadlines, but the goal is to minimize the worst case scenario. Okay. And so, in order to show that this is actually going to give us the right answer, we have to understand the structure of the optimal solution to the thing without knowing what it is. So let me define a notion. An inversion is where 2 jobs are scheduled in the reverse order of the deadline. Remember we said that we want to schedule the jobs in increasing order of deadlines, right? So in our solution, there will be no inversion by definition. We're always scheduling in increasing order. You don't have 2 jobs where one is scheduled before the other, whereas the deadline is later. That won't happen in our solution. Right? So the greedy algorithm will not produce the inversions. So what we need to show that our algorithm is correct is to show that the optimal solution has no inversions. Because if the optimal solution has no inversions, and we produce the same solution as no inversion, and in fact there's only one solution that has no inversion, which is sorting, it must be optimal. Okay? Yes?
But what if they're tied?
If they're, we'll talk about that.
Oh.
It actually won't matter.
Okay.
That's a good question. And we're not going to prove it just the way I said. We're going to prove it by saying, suppose the optimal solution has inversions. I can change it to another solution that does not increase the cost, which has 1 fewer inversion. So it's going to be, the argument for the proof is going to be a weird meta-algorithm on the optimal solution that doesn't actually exist. That's how the proof is going to work. So that's just step. So remember, the goal is to show that the key property of our solution, it has no inversions by definition, is what you need. Okay. And that's it. So first of all, 2 schedules with no inversions have the same cost. Right. This handles the tie-breaking situation. Because if there are no inversions, they only differ in scheduling jobs at the exact same deadline. Right? And the number of jobs is fixed. And so only the last job matters. Because one of these jobs is going to end. They have the same total, they have the same total duration, right? There's a total number of jobs which have the same deadline. You have to schedule all of them. One of them is going to be at the end. And that's going to give you the worst case. And that's why the worst case is what matters here. So for jobs with the same deadline, it doesn't matter which order you schedule in. So that takes care of the issue of time break. We don't care what it is. Okay? So that's the first observation. It's not the whole thing yet. 2 solutions with no inversions have the same cost. So what happens to solutions that do inversions? Could they have lesser cost? So here's the idea. As I said, we'll change the optimal solution to a new solution by removing inversions without increasing the cost. And we'll keep doing this. So it's again, it's an inductive argument, but backwards. In an original inductive argument, we said every step of the way we match what opt is doing. Here we're saying, well, opt did something, we did something else. But I can make opt look more like us step by step, till it has no inversions just like us. And we just prove that A2 solutions with no inversions are the same as. So this is the difference in the solution here. We are not saying that we match what opt does. We are saying that conceptually opt can be transformed into a solution that looks like ours without changing its cost. And therefore, since they have the same cost at the end, we must have them. Or less than equal. So this is the claim. If there in fact is an inversion to the optimal solution, they must be right next to each other. So imagine a solution that looks like this. This is an inversion because this job is scheduled first, but its deadline comes later. This is somewhere in the optimal solution, we don't know where it is. And they're not right next to each other. I claim that if this is the case, then there's some other pair that's closer. Why? Suppose the next job looked like this. Then we have a new inversion right here. And they're next to each other. Right? So then you can't have a job that ends right there. The next job has to end after, otherwise we prove the theory. So fine. The next job ends after. But now we have a new inversion here. Right? You see what happened? I said that there were two jobs that had an inversion and were not next to each other. So what happens next? Oh, these two form an inversion. Like, oh no, this deadline actually wasn't here. It was way out there. But now these two inversion. And the distance between these two jobs is less than the distance between these two jobs. That should be telling you induction. We've gone from a pair of jobs that are inverted and are x units apart to a pair of jobs that are inverted and are x minus 1 units apart. So we can repeat the argument again and again. And therefore, they must have an inverted pair that are x. So it's induction upon induction upon induction. Once we have shown that the optimal solution has an inverted pair where the two jobs are right next to each other, right? Then here's what we just flip it. Like opt has this pair, we'll just review over. So this is an example. Suppose you had this scheduled here, this scheduled here, and this was scheduled first, but its deadline was later than that one. This is the example that we found. Okay, we're just going to reorder them like this. So we go to this, first schedule that job, and then schedule that job. I could do something. So we start off with this and we go to this. Make them not inverted, essentially. That's all I'm saying. And what's going to happen now is the cost is not going to increase. I didn't say it will reduce, but it will not increase. Why? This is the lateness of the worst of these pair of jobs before the flip. Right? Just for these two. This is the lateness before they're adjacent. Right? And once you flip it, the lateness after the flip is this much. And you have to do some calculations to show this, but you can show the lateness will never increase. It will always either stay the same or reduce. And since the overall lateness, since I corrected myself, was the max of the individual latencies, if you reduce the lateness here, that cannot increase the cost overall. You can only bring it down or keep it the same. They could keep it the same if the overall max was not affected by this, or it could bring it down if it was affected by this. But it will never go up. So if the optimal solution had a pair had an inversion, then it must have an inversion that's adjacent. If it has an inversion that's adjacent, you can flip it and get a solution that's no worse in cost. So that you have one inversion less. Do it again, and again, and again. You're not actually doing this, your algorithm is not doing this, your proof is doing this. So your proof is saying if there's an optimal solution with inversions here, there's an optimal solution with inversions here, and there's an optimal solution with inversions like this, and no more inversions. Now I have an optimal solution with one less inversion. I do the same thing again, and again, and again, and again. I keep changing the optimal solution without increasing its cost till I'm like, hello Mr. Algorithm, we're right here with no inversions. And I have not increased my cost. So we have to have the same cost. The time doesn't matter. It's in the proof. The algorithm is not doing this. It's just you have a finite number of steps in which you can do this. Even the finiteness doesn't matter. And that's it. We have now proven that our algorithm is optimal, not by matching what the algorithm is doing to opt, but by saying that the algorithm stays still and opt walks towards it along a path of always decreasing cost, or always not increasing cost. So it's a very different kind of argument. It's using the structure of opt in a very different way. But nevertheless, it's saying that they are the same. Yes?
When you're comparing an algorithm with the optimal solution, it says that our greedy algorithm again creates a global optimal.
Yes.
So I couldn't find a way that if you prove a greedy algorithm is right and it is not global.
But that's not right, also. But that's not right. If it's not globally optimal, it's not right. It's incorrect. So you won't do that. I feel like I've misunderstood your question. But we talk about I don't think I've answered your question satisfactorily. Yes.
How do we know that flipping an inversion doesn't produce an inversion somewhere else?
That's a very good question. How do we know that flipping an inversion does not produce an inversion somewhere else? It's because these two are adjacent. If they're not adjacent, then you're right. Flipping it will cause all kinds of havoc. But they're right next to each other. The flipping only affects the two of them. This is the optimal sequence, remember. Right? Everything else comes afterwards and everything else comes before. These two are local to each other. So flipping them locally does not change anything else. You are absolutely right if they weren't, which is why I had to do all that work to say, oh wait, they're right next to each other. Otherwise it would not have worked. And that's a very important step, because as you're observing, I have to be able to reason that I decrease the number of inversions in every step. This doesn't work. So it's very good. Okay. We'll continue with more greedy algorithms again in the notes on Tuesday. I will put up these slides, so I know some of you are taking stuff. I will put the slides here. Yes. Oh, and choose the